All right, so let's get started. All right, so I still need to, so this is what we did yesterday, the introduction to acoustics. What did we do before that? I think we did all this stuff yesterday, 114.
Yeah, we did go through a lot of pages yesterday.
Yeah, but it looks like I have a repetition here. Oh, so already went through 114 here, 113. Oh, okay. We're gonna change the order here. All right, I think these are all the pages from yesterday, so let me keep these ones. Yeah. Yeah, all these pages went yesterday, but I think went before through these ones. So we need to scan them. All right, so we have to do a lot of scanning. I mean, not a lot of scanning, it will be just one file, but. All right, so let me try to catch up with you guys here on videos. I'm gonna try to do both things at the same time. That way you will see how long it takes to do those things. I'll control delete. So I have no idea what one I use. University one, I guess. No idea about my password. Oh, really? Oh, lucky. So what I would say, done. So I just have to move the file, just did that on the room order. Videos, June 19, I think it was yesterday. Open. So this was vibrations, but intro to acoustics. Acoustics. Wave equation. Alright, publish. Alright, now I will do that at the same time. I don't forget to do it. Okay, then I can go here and do it. Alright, so let's go back to the notes. So yesterday we started the acoustics, and basically, what do we say? Is that in order to have acoustics, it's not that much, it's not the vibration of the string that really creates the noise, it's the way you disturb the medium or the air molecules that create the noise. Okay? So for example, if you have a musical instrument, you can play it on earth because you have a medium called air, but if you go to space, you're not going to hear anything. So it would not be a good thing if somebody asks you, what would you take to space with you? And say, my guitar, no? Would be a little bit useless, okay? So anyway, so we said that obviously then everything that you disturb creates a wave, okay? And that the waves travel at what speed? The speed of sound that we say is about 350 meters per second. And we try to make an analogy. It's like if you do about 3 football fields or even a little bit more within 1 second. Okay? That's how fast that wave can travel. But it's not that much that this travel is because you disturb one little molecule here, and this molecule will disturb the next one, and so on, no? That it can move so fast. So we went through the equations. We say, what is the approach we're going to use in order to solve the differential equation? We know the solution is in function of x and t, 2 variables. So we assume that the total solution is going to be the product of one function in x times one function in t, okay? Phi and t. Doing this, we do the substitution, and we obtain this equation. Now the trick is to say that these two needs to be equal, and these are also going to be equal to one constant value, which is known as the eigenvalue, which we have over here. So by doing so, we are able to define two different differential equations. Both of them should be equal to the same constant. Okay? So now, yesterday we solved first this equation, and what did we find out? We solved that equation for this type of problem, where you have one string, simply supported, just attached at both ends. So what could be the solution? The simple solution, we say, will be, after a bunch of algebra, so by looking at different cases, we say that the solution will be of the form what? Sine n pi x over L, which represents what type of motion? The string either can move in this form, if n equals 1, will be the full sine wave if n equals 2. If n equals 3, you will have 3 of those hills, no? Or valleys. If n was equal to 4, you will have 2 full cycles of the sine function, and so on and so on. Alright? So the general form of the solution was of this one, Bn sine n by x over L. Okay? Well, what is Bn? What is really Bn? Physically.
You need to.
I mean, it's the amplitude, no?
Mhm.
So we're going to have to determine this one. So the other equation we needed to solve is the one now in function of time, which is 1 over h, second derivative of h dt equal to minus lambda. All right, so let's do that. So let's see here. Continuous. Next page. Today is June 20. Page 125. All right. I'm going to be doing now is solving the equation here. So next, let me use different colors. Solving. Now, what was the second equation?
I think it was h double prime of t over h of t equals negative lambda.
Okay, equal negative lambda, or which is the same, second derivative of h dt squared plus lambda h equal to 0. Okay, so we already did this problem, so we need to solve this equation, but now we're going to save some time. So we are solving this problem for what type of string? This one over here. Okay, we can move the other, we could be the other one. All right, depending on the solution, but we know it's that type of problem. So we already applied the initial the boundary conditions. This time we're going to say the initial conditions will be u of x at 0 will be u sub naught, or sorry, this will be for h. So h at 0 will be u sub naught, and the velocity, so dh dt at time equals 0 be equal to v naught, or u dot 0, okay, which is the same. Okay, how do we find the solution of this equation? What is the first thing?
You assume a solution of some exponential.
Okay, so assume harmonic solution. So this time we say h of t would be equal, let's say, to h sub naught e. What do we use before? Sx, no? We use st. Okay? Next, what do we do? So the second derivative of this will be equal to what? So dh dt will be equal to h sub naught s e s t, and the second derivative will be equal to h sub naught s squared e s t. So second step, we substitute into the differential equation. Okay? So what are we gonna get? So we get h sub naught e s t. This will give us what? S squared plus lambda equal to 0. Okay? And like always we say about the equation satisfied is what? If this is equal to 0, what does that mean?
It's a trivial solution.
So the trivial solution. Or what is the other option? The s squared plus lambda to be equal to 0, which this one gives, so s squared plus lambda equal to 0, which means s squared equal to minus lambda, which means s equal plus minus
Square root of negative lambda.
yeah I, because negative of minus 1 is I, no? Same as before. Okay, so that gives so I have the general solution, so 126. Oops, forgot to budge. So I'll put it down. It's 126, the general solution, the solution for h of t becomes, so h of t will be equal to what? h1 exponential of minus I omega t plus h2 e I squared over omega t. Okay guys, so we're not going to redo the whole problem as before, because before what do we say is that the solution will depend on the value of lambda, no? Okay? But when we solved this problem before, what did we find out? So first we solved for
lambda being negative.
lambda being negative. And we find out that this solution had
No physical meaning.
no physical meaning. We find out for lambda equal to 0. We find out this one had no physical meaning. And then at the end we decided to solve for lambda positive, no? So in this case, what is the only case for lambda we're going to consider?
Positive.
lambda positive. We don't need to redo everything again, okay? But let's just say here, for lambda positive. Okay. So for lambda positive, again, we're going to use the Euler relation. Which are what? Ei omega equal to cos omega plus I theta So this is, and we did that last time, but so h of t becomes what? h1
Cosine of square root lambda t
lambda t
minus I sine of square root lambda t.
lambda t plus h2 So if we collect terms, we're going to have h1 plus h2 cosine square root of lambda t plus h2 minus h1i sine square root of lambda t, or ht equal to c cosine square root of lambda t plus d sine square root of lambda t, where c equal to h1 plus h2, d equal h2 minus h1i. Okay, why did I use the letters C and D over here?
Because A and B are already used for phi.
Because A and B, we already use them for phi of x, which is over here, no? All right, basically we are the same thing. Then we solve for lambda, okay? Oh, since we are doing this, and what is lambda?
Would be the
Lambda is the one we solved before, which would be, let's see what that is, would be n pi c over L, no? Okay? So from page 123, so n pi c over L, see page 123.
Was that lambda or the square root of lambda?
Is the what?
Was that expression lambda or the square root of lambda?
Square root of lambda.
Okay.
Okay, so all right, so let me do this in detail. So really, okay, so what we're going to do now is replace this one over here, but I'm going to do two steps at the same time. What was the general solution? What was our general assume solution was u of xt would be equal to what?
Phi of x times h of t.
Phi of x times h of t. So now we have the expression for phi of x and for h of t. So we can go to the next page. I'm going to do that in detail, it's fine. But I might need your help because you probably have a lot more accessible the notes than me. Okay, so where phi of x was equal to the summation b sub n sine n by x over L, no? Okay? And h of t, so if I substitute will be equal to what? C cosine of n by c over L t plus d sine n by c over L t. Okay, so that means that the total solution, ux of t, is equal to what? Summation of bn sine n by x over L
Times all that.
Yeah, what I'm trying to do, if I don't have space over here to write it down, so just do the first term. So C cosine n by c over L t plus d sine n by c over L t. Okay? Or us of t would be equal to the summation to the sine n by x over L times an alpha n I define now cosine n by c over Lt plus beta sub n sine n by c over Lt, and you close the bracket. Where alpha n will be equal to what?
B sub n times c.
B sub n times c sub n, and beta sub n is equal to B sub n times B sub n. Okay guys, does it matter if I change the name of the constant?
Not really.
That's just constant, no?
Mm-hmm.
You can call it a plus b or a minus b or c, whatever you want. At the end of the day, they're just constant. Okay, so now what do we need to do? What do we need to do at the end then, in order to have the complete solution?
Use the initial conditions to.
We need to determine that alpha sub n and beta sub n, no? Okay, and this is going to be a little bit involved, but So next step is next alpha sub, so the constants alpha sub n and beta sub n are determined. Trying to see if I can find a shorter way to do this, but it doesn't look like. All right, so let's see. Page 128. So we needed to, so now using the initial conditions, so what were the initial conditions? Actually, we wrote it in two places. Let's see what they are. We wrote them over here, no? In function of u, so this is the one we need because we have the final solution. So what is the first initial condition? U of x at t equals 0 is equal to u sub naught. So one is the velocity at t equals 0 equal to u dot sub naught or v sub naught, okay? So these are using the two initial conditions. So we have u of x at 0 equal to u sub naught, and du dt of x0 equal to, you want to use u dot sub 0 or v naught sub 0?
I think V naught's cleaner, less confusion.
Okay, v naught sub 0. Okay, so let's remember, here we could do the maple, but I don't think, let's do it the hard way. So we have the equation on top. The first boundary condition will give us what? So let's see, the first condition is u of x0 equal u sub naught. So we substitute the t equal to 0 to over here, what do we have? U of x0 will be equal to the summation of sine n by x over L. And then what do we have?
Alpha sub n plus 0.
Plus 0. So, and this should be equal to u sub naught. So basically it's going to give us what? I mean, we could move the factor up sub n, so summation of alpha sub n sine n by x over L equal to u sub naught. Okay, so I'm gonna do one by one. I'm gonna change something here. So now, I'm gonna write down, all right. Using, and this is extremely important, the orthogonality property of the sine function. So I give it to you and then we discuss it. The other condition says that if you have sine n by x over L times, let's say, sine n by x over L dx, this is equal to 0 if n is different than m, and this is equal to L over 2 if n equal m. Where obviously n and m should be what? Can they be any real number?
Yeah, it should be any integer.
Any integer, but that's not any real number. So it's either 1, 2, 3, 4, 5, 6, 7, 8, whatever, no? So all this stuff really depends on what? It's just telling us where we're going to go on this circle, no? Okay? All right. So this property is extremely important. And we're not going to get into detail now, but that property is also validated by the eigenvectors. They follow the orthogonality property. And that has a lot of advantages because we're not going to get there, but if you apply this then to, let's say, a couple equation, to a couple differential equation, you can decouple differential equation just by using this property. Okay? But we're not going to get there. So we use this over here. What do we need to do to this equation in order to solve them for alpha sub n? So let's say we take this equation here, okay? So recalling star equation. And what we're going to do is multiply both sides by sine n by x over L. Okay? So what we're going to have over here, we're going to have integral, let's say first sine n by x over L, and now put the one we have over here, which is summation of alpha n sine n by x over L dx. That should be equal to what?
The integral of sine n pi x over L times u naught.
Yeah, u naught sine n by x over L dx. So obviously, what is the case that we're interested over here? For m equal n, this should be equal to what?
L over 2 times the sum of alpha n.
L over 2, if you want just alpha n or summation of alpha n. Correct? And this should be equal to what? To the integral 0 to L u sub naught sine n by x over L dx. So finally, what's going to be alpha sub n? 2 over L, integral 0 to L,
mu naught sine of n by L, or n by x over L.
sine n x over L dx. Okay, so let's to do an example. This is not even the class notes, but I mean, I said on the original class notes, but let's just draw an example. So for example, if n equal 1, what should be the interval? That way we can solve for n equal 1. Do you want to do that now or at the end we solve everything for n equal 1? Maybe we can solve this final solution at the end for n equal 1, no?
All right.
That way so we have this one. Now we need to follow the same process that we did over here. For what? For the second boundary condition, no? The second boundary conditions will be over here. du dt at 0 equal to v naught. All right, so let's see, where was our expression for, so we need to do du dx dt. All right, so let's see, what is u of xt? We had summation sine n by x over L alpha n cosine n by c over lt plus beta sub n sine n by c over lt. Okay, so what would be du dt?
Let's see.
So we don't have to deal with the summation of this one, no? This is in function of x, no? So n by x over L. And now over here, what are we gonna have?
Negative alpha n times n pi c over L.
Negative alpha n.
It should be times n pi c over L sine of n pi c over LT.
Yeah, but I'm just thinking here, I'm a little bit ahead with that. Okay, yeah. So minus alpha n by c over L sine n by c over LT plus beta sub n by c over L cosine n by c over LT. Okay? So now the boundary condition is at what? It's at t equals 0, no? So at t equals 0, if you want du dt of x 0 really would be equal to what? Function of sine n by x over L. And then what are we going to have over here?
beta n pi c over L cosine.
Beta n, no? So this term here becomes 0, no? The first one.
Mm-hmm.
And then we have beta n pi c over L, because this becomes 1. And all this should be equal to what?
Beta.
Beta. So now, what are we going to do? What did we do before?
Multiply by sine of m pi x over L and then take the integral.
Correct. So applying the orthogonality property, what do we have? Integral of sine m by x over L, summation of sine n by x over L times beta n by c over L. But all this is a constant, no? Doesn't change anything. Dx. This should be equal to what?
Integral of v naught sine m pi.
Yeah. Sine m by x over L dx. So for m equal n, what would be all this term equal to?
The summation of 2b n pi c.
So all this would be L over 2, no?
Mm-hmm.
These two terms. And then we have, yeah, b sub beta sub n by c over L will be equal to v sub naught integral of sine n by x over L dx. Or this will give beta sub n equal to
So it would be
What?
2 over n pi c, or sorry, 2b naught over n pi c.
2v naught n by c
Times the integral.
times the integral of sine m by x over L. Yeah. But remember that n equal m, no?
Mhm.
So we're using both notation, but so this is what will be a class of partial differential equations. Okay? That's what you'll be doing a full semester. For the heat equation, which is the Fourier equation, the wave equation, and what is the other one? Forgot yesterday as well. I know there's 3 types of equations. Wave equation, heat equation, and then there's one of structures. I remember now. But anyway, it will be all the time the same thing for different boundary conditions. Okay? Just so I know. So let's just do as an example now for n equal to 1, no? Okay? So let's see what that will give us. So page 130. So we have this problem over here. What is the physical problem we are solving?
Vibrating string.
Vibrating string, and let's just solve it for n equal to 1, no?
Right.
Okay? So In that condition, let's see, what is alpha n? Alpha n was equal to, it's over here,
There we
2 over L sine n by x over L dx. We assume that u sub naught is constant, so alpha n equal to u sub naught over L integral 0 to L of sine n by x over L dx, which will be equal to what?
go. 2u naught over pi.
So it will be L over n pi, no? And then cosine of n pi x over L between 0 and L.
Actually, I think it would be the negative of that.
Why no? The cosine gives sine, no?
Yeah, but the integral of sine should be negative cosine.
Yes, because this gives negative, so it should be negative. All right. So let's see. This will give us what? Alpha n equal to, let's start simplifying a little bit. So n is equal to 1, so we can put just 1, okay? So this L will cancel with this one, so we get what? Minus 2 u sub naught over pi. And here what we're going to get? Cosine
of pi L over Lx.
of pi, no?
Okay.
Because the L will cancel out.
And minus 1?
Minus cos of 0. So that gives what?
Minus 1, so should be negative 2.
So it gives
Inside the brackets.
minus 1. So yeah, this is equal to minus 1 equal to 1. So this is going to give alpha n equal then to 4, no? U sub 0 over pi. Okay? But we're solving this part where the string is just vibrating at that frequency. So, all right. The other one, let me take another page. Well, okay. We continue on the next page. Beta sub n was equal to 2 V naught divided by n by c, but we know that n will be equal to 1. So really here I could put alpha 1. To integral of sine n by x over L dx. So we can go a bit faster, no? Here. So let's say beta 1 will be equal to 2 V naught pi c. And this should be equal to what? Minus
L over n pi.
L over, let's say just say pi because it's equal to 1.
Alright.
L over pi
Times cosine of pi x over
cosine
L.
of pi x over L. So beta 1 equal to 2 V naught pi c, oops, minus 2 V naught, 2 V naught pi c pi squared of what? The same as before, no?
Yep.
Cosine of pi minus cos of 0. So at the end we have
4 V naught L over pi squared.
$131. We have that. Oops. beta 1, so remember this is equal to minus 1 and 1. So we give us 4 V sub naught L divided by pi squared C. Okay, the total solution Ux of t, which is which one? This one over here, no? That I use over here. So this will become what? Ux of t for n equal 1 will be equal to what?
Sine of pi over Lx.
Sine of pi x over L times, I'm just going to put the alpha 1 this way,
Alright.
cosine n pi c over Lt plus beta 1 sine n pi c over Lt where alpha 1 we found was equal to 4 u sub naught over pi, and beta 1 4 v naught divided by pi squared c. The end.
That's all hoax.
Yeah, those programs take a long time, no? So basically, guys, right now, I'm probably not going to do it because I want you to concentrate on the problem, but what is we solve what type of problem? This one with this type of boundary conditions, no?
Mm-hmm.
So what I can do next? I could give you, for example, to solve this one, no? Yeah? Or I could give you, and then this one to be on some type of slide. I can just move up and down, no? I mean, there's different combination, but the procedure will be the same. So in this case, what will be different? We did this one. What will be different about the boundary condition about this one? This will still be what? U of whatever. U at L will still be 0, but here, what would you have to say? Because this is one says what? U of 0 equal to 0, no?
Mm-hmm.
But what would you say for this one? Would you say the same thing? What is the biggest difference between simple supported and clamp? The best way to do it is to plot it.
So the slope at that point will be 0 too.
The slope, the point at that slope will be 0. Okay? So this one must be satisfied, but in addition you need to have this one, no? Which makes it different. Okay? Then this one, what would you have? I don't know, like U of 0 equals 0, but here what would you have? U at L might be just in function of y. Let's say a y, no?
Mm-hmm.
And you just solve with those things. You follow exactly the same procedure, but you will end up with what? Different coefficients, no? Alpha n, betas of n,
Mm-hmm.
and so on. Okay? If you want to be more complicated, you could put this one instead of being constant, this one could be in function of the deformation, no? Of x. So then when you do the alphas of n, it becomes a bit more complicated. But that's basically what would be a class in partial differential equations. And acoustic, basically, you do exactly the same thing, but the only thing you do is that you replace that constant c over here by pressure p. Or the u, instead of being the deformation, will be pressure. Okay? So we look at what is the change in pressure at the different places. And you will be solving that equation for all those different cases. All right? So let's see, let me organize these class notes. So 131, so how many pages we have for this one? I lost 129, I guess. No, 129, 128, 7, 6, 4. And I guess this one goes to 123. Yeah. Okay, so I don't want to cover really anything else about acoustics, okay?
Alright.
Because it's all like that. So now what happens is that we can do specific cases, the specific cases where you can solve that equation. For example, we could do that equation, for example, this thing about a wave that is going to reflect on a cylinder. Okay, the wave, how it's going to reflect on the cylinder. You know the equation of the cylinder, no? So you can put that as the boundary condition. And you can solve that differential equation for that. But it's just mathematics and doesn't add much to it. Okay? However, since we have time, and I know how to do it, but I've never done it with MATLAB under those conditions. So I will scan all these things today after class, and I will plot them, okay? So from page 95 to 135, that's where we have this. But something very useful that I think you should learn how to do, and let's see if it can be done with the ODE 4.5. I know I've done it in the past with MATLAB, but I had to program my own ODE. So that count. Let's put it here. So really, now what I think will be extremely useful for you guys is that, all right, from the vibration equation, now we have learned that the general form of the vibration equation will be of this form, okay? So what happened is that, yes, we solve for base excitation, where basically this is in function of y, no? Of the base. But basically they all end up on the some type of this form, okay? And we solve this problem for f of t only as the form of an harmonic function. Okay? Because why? Why could we only solve for an harmonic function? Let's see if you really understood the procedure.
Because that way it would be simple enough to do by hand?
That's why. But basically remember, in order to be able to simplify, we needed to assume here, okay?
Well, it was helpful that the exponential terms would cancel out.
Correct. So, and this will only work if you give some type of sine or cosine function or exponential function. So all those solutions we found on the closed form solution will be for some type of sinusoidal form. Okay? But f of t could be of what form?
Technically anything, probably.
Could be something random, no? Could be more like a step load. Okay, any type of load that you want, no? Could be a combination of sine with a noise or whatever you want. Okay? So what about trying to, let's say, we can get a time history of this one and just try to solve this equation numerically for any type of load that you might have the time history. Okay?
All right.
So that will be the goal to do now, but I don't know if it can be done, okay? We're going to have to do a Google search or whatever you want on MATLAB. I know because the problem of the ODE45, that was a long time ago when I tried to do it, the ODE45 or the ODE23, you could not determine the time step. The function itself, the ODE43 command, will try to select the best time step in order to get to the solution. So what is the problem then? Is that when you generate this function over here, what is the time step you're going to be using? Because you have to, when you generate this load, you need to tell him where to put the points, no? Correct? Yeah, so if he takes one point at each place, it's fine. But what happens if MATLAB can take this point and then let's say a point over here? He's missing those two peaks, no? So he's doing whatever he wants. So hopefully they were able to resolve it. Okay? But we have to do a Google search. So I'm telling you right now, I haven't done it. So, but it's something that could be done, no? I'm guessing. I hope now it could be done because why not? So what could we type over here? Oh, let's see if that one was over. Yeah. So let me do this now. What is the 8? So last time was June 19 yesterday?
Mm-hmm.
Sorry.
Your blessing.
Thank you. So we have this is the video. And save. Okay, good. All right, so what can we search here? MATLAB solve ODE for time function. No, for time generated load or force. There we go, with time dependent parameters. Oh, I want to interpolate now. So my ODE function, what is my ODE here?
It looks like it's one he wrote.
Where is my ODE?
I think that's the function file for making that function.
And then it's here. So is this one calling another function, no?
Mm-hmm. I think so.
Yeah, but ours is even simpler than that. We don't need, we just need this to pick up. So where's my ODE in there? Is this is where it is?
Yep. At least that's what it looks like.
So what do you want to interpolate here? Let's see. F of each of two. dependent force. And it should not be that complicated. Yeah, they want you to decorate no matter what. Huh. Okay, we have to try. You want to do this as homework? It could be good, huh? Okay, will not be mandatory. One will be extra, okay, if you want to do it. Let's do this as homework. Let me just give you homework.
All right.
And I'll be the one generating the function if you want. So, optional homework. Credit. Okay? Write a MATLAB code that must be able to solve the following equation of motion, which is mx dot dot plus cx dot plus kx equal ft for a time dependent force. And then you generate the time dependent force for you. Let's see. Home, computer. Let's see if I still remember how to do those things. I should go and play sometimes with MATLAB again. Just play with you in class. It might not be enough. So is it not working now? Okay, something went very wrong here. Now nothing is working here. .com is not working, no?
It's not up here if that's what you mean.
Not doing anything. I have it on .com here. Not doing anything. Computers, not doing anything. Laptop, okay, let me turn everything off. Not showing anything, no? Okay, this is funny because I don't know if it's the projector or not.
Projector is on.
Huh?
The projector is on. and it did the intro, Panasonic and everything, it just shut off afterwards. Or I guess it didn't project anything.
Subtract on the flag a few times, took it down using aircraft shadows. It took it down. Those stories.
So another project is something, I think.
Maybe did a cable get knocked loose somewhere?
The cam. Computer. Cannot even see on the computer. My computer screen is.
Oh, well, that's probably why. It's showing the computer screen, which is black also, so.
Maybe
Yeah,
did-
but when I go to .com, also not showing anything.
Is the modem on? Maybe it kicked out?
I don't know. I mean, the things I cannot see anything on the computer. You want me to restart the computer? Or?
We could probably do that.
The computer is making a weird noise. It looks like the fan is almost gone.
Maybe it overheated or something. I don't know.
Okay, basically what I was trying to say is that, so when we need to check, if it's going to be too high or not too high, it's going to be, what I want you to generate is, let's say, some type of loading. So let me come over here. Let's say some type of loading that will be a combination of, let's say, a sine wave, all right, and some noise, okay? So this should give you what? Either this one is going to be more dominant than this one, okay, but if it's something in between, you might end up having, I don't know, something like this, no? And I wanted you to solve something like that using the MATLAB. But I wanted to see if we could generate that very quick, or at least give you the commands. So, I don't know what to tell you. The screen here is completely gone. I just restarted this. Oh, I did not see anything. Okay, so I don't know, this should not be that difficult to be able to generate. I'm kind of guessing a little bit. This, you can just generate this with whatever, you can say x equals 0 to whatever, 0.1 to what, 10?
Sure.
Doesn't matter, use 4 cycles, no? Doesn't need to be a lot. And then this one, Johnny, you could say x equals some type of random nodes. I think it's rand n for random normal distribution. And then here you can say the number of points. So I don't know how many points is that going to be. That's going to be what? 101?
Should be 1,000.
No, from 0.1 to 1 to 10 would be 10 to 1, 100, no?
Yeah, 100, yeah.
So 100, 101. So you could say, I don't know. I don't know if this is 101 or use a multiple of 4. You know, 144. This works all the time better if it's 2 to the power something. These types of command. But try to see that it's the same size or whatever here. I think this can work, okay? Or 101. And then you just add these two together, okay? And see what you get. Obviously, if you only get this, it's not going to be too useful, no? Try to get something in between. Play with those parameters. Put a constant over here if you need in front of this one. So you can write just, sorry. That will not be x1. This will be your x. And your x1 could be here just sine pi x, no? Okay, and you add it together. Let's see if this is on. No, monitor is still on.
Yep, probably that.
So, yeah, but the dot com computer is gone, not doing anything. All right? So I wanted to see, but this should not be that hard. Just try to generate a random node. I don't care what just f of t, but that when you plot it, it's not, I mean, it's not something that you can integrate easily, no? Only numerically. And then just write the ODE for that type of function. Okay, so what's going to be the problem in this? We'll talk about in 5 minutes. What's the problem is that right now we have the load. Maybe that would be the way to do it. Yeah, I'm just thinking. But what happened is that remember we had on the main function we had ODE for 5, found solve for whatever, YT and T span, and here we have YX or something like that for the solution, no? And within the ODE, we put all those parameters, and we put the loading. What happens is that here, at each time step, the loading is going to be different. And the stuff is that the ODE changed the time step by itself, so you need to make sure that it's going to take the right value. I think I see now what they're doing. I think right now what they're doing is that they're generating the load outside. Now I understand what they're doing. And what they do is that they put here like my ODE. Okay, so what my ODE does is that at the time step of the ODD for 5, so let's say you have here a value of t equal whatever, 2 seconds and t equal 3 seconds. But the time step is the ODD for 5 decides to take at that time is 0.5. Okay, so what the interpolation is doing is finding a linear interpolation of your loading at 2.5. Okay, I think that's what it's doing now. I think that's why it's doing those interpolations. It would be good if you could specify the time step, no? That way it would be a lot faster. It would be very easy to program. I mean, and that is very useful because then you can solve any vibration problem, no? Without having to do the numerical, the hand calculation. You could solve it just numerically.
Sounds good.
Which at the end of the day is what you want to be able to do. Okay, all those by hand calculations, I'm not going to say are not important, but they are important in order to understand what you're solving. But once you understand what you're doing, the only thing you need to do is to find the solution quick. Okay? Instead of going through all the hassle of all the algebra. And by hand calculation, you can only solve very easy cases. Okay, you can solve this one, you can solve it by hand calculations, but then you need to go to stochastics, algebra, you will not like it. Okay? So basically you need to do integrals, probabilistic integrals, which means I don't know what it's going to be, but I can estimate that it's going to be somewhere in that area. Okay? However, you do that numerically and you find the answer very quick. Okay? So I don't know, do you want to have class tomorrow? Or? Yeah, we can do that tomorrow. Okay, we don't know how long we're going to be, but so let's see if tomorrow this is working and we can see if we can generate the load at least. Is that okay?
All right. And so
It might be a short class, but
all right. And so the optional homework due same time as the exam?
just do the same time as the exam.
All right.
And then just double check, so you want us to go ahead and do the OE45 function to be able to generate the solution to the third.
Yeah, something, so I don't care if it's exactly that one or not, but something
Right.
that is random, okay? Something that
Right.
you cannot get the solution easily. Okay? That would be very useful if you're able to do it. I don't see it's very complicated, but it's probably you need to sit down and look at it.
All right.
All right, so I did